Section 8.7 is really an application where we take our understanding of momentum and center of mass and apply it to rocket propulsion. Our objectives here are to use conservation of momentum to explain rocket motion and use these equations for thrust and velocities to solve some problems. So how are rockets actually propelled into free space or in a vacuum when there really is nothing to push against? It's not like taking a step and you can push against the ground. There is nothing out there to push against. The answer is based off of the conservation of momentum, where your system is now the rocket plus the ejected fuel. And just like we said an archer on ice would move backwards when he fires an arrow, a rocket is going to move forward when it ejects fuel out the backside. When we look at the archer example, the arrow would have some momentum in one direction, its mass times its velocity. So to conserve momentum, where the initial momentum of the system was an initial momentum of 0, the archer must have an equal and opposite momentum. Same exact amount of momentum, but back in the opposite direction, so that the total momentum is still a 0. If you could imagine this archer, maybe as an elf that just has this unlimited number of arrows coming out of his back, where he can keep firing more and more arrows, every additional arrow that he fires is going to cause the archer to gain more and more momentum in that opposite direction, moving faster and faster. The rocket basically works this way. And so if we think about the rocket as, expelling this fuel out the backside, with every little bit of fuel that's expelled out the backside, and the amount of momentum that it gains going in that opposite direction, the rocket is now going to gain a momentum in the opposite direction that's going to perfectly be counterbalanced by these small little bits of mass from the exhaust gas and their momentum being fired backwards. Really, this is kind of like the opposite or the inverse of an inelastic collision, because momentum is conserved, but kinetic energy is actually increased. Where is it coming from? It's coming from the expense of the energy stored in the fuel. So the rocket initially has some velocity v. Well, it contains the mass of both the rocket itself and the mass of all the fuel that it's carrying. We'll call those values m and delta m. So during a short time, call that some time t, the rocket expels this fuel, and the speed of the rocket is now going to be increased to some initial velocity that it had, plus the extra boost or change in velocity that it gets from expelling the fuel and gaining that forward momentum. Now, if the fuel is ejected at a velocity v sub e relative to the rocket, the speed of the fuel relative to a stationary reference frame would be v minus v sub e. So if we look at the total momentum before the gas is expelled, we'd have the total mass multiplied by its initial velocity. And afterwards, we now have the mass of the rocket moving at a new velocity where it's gained this little extra boost of velocity from the forward momentum, and we have the momentum of the fuels and the gases that are being expelled out the backside. So there's its little bit of mass and its velocity that it's moving at. This basically boils down to this equation that we have right here. Now if we look at that equation and take the limit as the time approaches 0, so we look over a very small amount of time where the velocity would have some infinitely little small change in velocity, or dv, and the mass would have some infinitely little small change in mass. We could write this as the exhaust mass now corresponding to the mass lost by the ship. So this little dm could really be written as a negative d capital M. And now we could rewrite the equation that we have up here in terms of dv's and dm's instead. What we can do with this equation is integrate it. Basically, what we have here is a differential equation where the variables are already separated. So if we integrate each side, we can integrate the side with dv to find a value for the final velocity of the rocket. And we can also integrate the side over here with m, where the integral of 1 over m is basically a natural log function, or the natural log of m. Plugging in your limits of integration, you get the equation that we see right here. Notice that the final speed of the rocket is proportional to the exhaust speed. So the faster you shoot the exhaust out the backside, the faster your final speed of your rocket will also be. We can even link this to force or thrust. Thrust is that force exerted on the rocket by the ejected exhaust gases. So if we take the derivative of this initial equation up here with respect to time, instead of integrating, we could find an equation for force. Because if we take a derivative here, a derivative of v with respect to t is really an a. So we end up with ma, and we find that this force from thrust is equal to the absolute value of ve dm dt. Let me show you how to use this now in an example. So let's look at an example of this. We have a rocket in free space that has a speed of 3 times 10 to the third meters per second. Its engines are turned on and fuel is going to be ejected in a direction opposite the rocket's motion at a speed of 5 times 10 to the third meters per second relative to the rocket. The first question is, what is the speed of the rocket once its mass is reduced to 1/2 its original mass? So if you remember on the last slide, I gave you this equation for the final velocity of the rocket. It was Vf minus Vi equal to Ve times the natural log of the initial mass over the final mass. So we're going to plug in some of these values. We're looking for the final velocity of the rocket, so that's what we are solving for. The initial velocity of the rocket was 3 times 10 to the third. The exhaust velocity was 5 times 10 to the third. And we want to take the natural log of the initial mass divided by the final mass, where the final mass is exactly half of the initial. So basically we're looking at a natural log of 2. Go ahead, pause the video, plug this stuff in, and see if you can solve for the final velocity of this rocket. You should get about 6.5 times 10 to the third meters per second. The second question asks you, what is the thrust force on this rocket if it burns fuel at a rate of 50 kilograms per second? Remember from the last slide that thrust is equal to the absolute value of the exhaust velocity times dm dt. Ultimately, what we can plug in here then is that exhaust velocity of 5 times 10 to the third multiplied by that dm dt, or the rate at which the fuel is burning, which we said was 50 kilograms per second. Multiplying these two things together, we find that that thrust force would have to be equal to about 2.5 times 10 to the fifth newtons of force.